Hello everyone, and welcome to today's lecture on software reverse engineering. In our previous session, we focused on the initial development lifecycle. Today, we shift our focus to what happens after software is released. We'll explore why software evolves continuously, the significant costs associated with that evolution, the challenges of recovering a design from legacy code, and what our current suite of reverse engineering tools can and cannot actually do for us. Let's start with a practical example, the altimeter, which is commonly used in aviation. For those who are unfamiliar, an altimeter is a flight instrument that measures the aircraft's altitude above a fixed level. Reliability is paramount here. Look at these two code snippets. On the left, we see a legacy-style implementation using go-to statements to handle sensor failures, while on the right, we have a structured if-else approach. As computer scientists, we look at the snippet on the left and see spaghetti code. But before you decide to refactor it, you must ask, should you? If the go-to version has been flight certified for 20 years without error, is the risk of introducing a bug during refactoring worth the cleaner code? Furthermore, look at the default value of 3000. Is that a safe altitude? Without domain knowledge of where the aircraft flies, we can't even tell if the logic is correct. So why do we care about this? Because software evolves continuously. If we look at the distribution of maintenance efforts, we see that user enhancements, adding new features, takes up a massive 43% of the pie, while adaptive maintenance, changing for new environments, is 25%, and corrective maintenance, or bug fixes, is 21%. Note that preventative measures and efficiency tuning are very small slices, which are 4% each. This means the vast majority of our work is reacting to change, not just fixing mistakes. To understand this better, we look at Lehman's programming types. The first type, or the specifiable type, are programs where the problem can formally and completely be stated, like a mathematical function. Acceptance is simple. Does it meet the spec? The P-type, or the problem type, being our second type, address real-world problems that are imprecise. The solution is never perfect because the world changes. Finally, the E-type, for embedded systems. This software becomes a part of the world it models. Think of a banking system. It doesn't just calculate interest. It is the banking process. These are inherently evolutionary because the software and the world constantly affect each other. These diagrams illustrate the loops of change for these types. In S-type, you have a formal statement that leads to a program. In P-type, you have an abstract view of the world that leads to a specification. But the real world can change, forcing you to compare the solution and restart the loop. In E-type, the program is inside the real-world cloud. Any change in the world forces a change in the program, and importantly, the program itself changes the world, creating a continuous feedback loop of requirements. This leads us to Lehman's laws of program evolution. Law 1. Continuing change. An E-type system must be adapted or it becomes less useful. Law 2. Increasing complexity. As you evolve software, its complexity grows unless you actively work to reduce it. Law 3. Self-regulation. Evolution is self-regulating, with measurable trends. Law 4. Conservation of organizational stability. During the active life of a software system, the work output of a development project is roughly constant, regardless of resources. And Law 5. Conservation of familiarity. You can only change a system so much in one release before the developers and users lose their mastery of it. If you grow too fast, quality drops. Now we move on to the graph that shows why we are always behind. The green line represents user needs, which grow linearly over time. The red line represents conventional development. Because of the time it takes to identify requirements and develop the first release, we start with lateness. As we release, we have a shortfall between what the software does and what the user now needs. The shaded area is inappropriateness, the gap that leads to the eventual replacement of the system. Now let's look at real-world data. This is Logica Financial Software, a visual, collaborative financial modeling software designed for dynamic planning, budgeting, and forecasting, measured by its size in modules over several release sequence numbers, or RSNs. You can see a steady, almost linear growth. This confirms the law of continuing growth. To keep a financial system viable, you must keep adding modules to handle new regulations, markets, and features. The Linux kernel provides a more dramatic example. From 1994 to 1999, the lines of code didn't just grow, they grew exponentially. In a complex OS kernel, as you add support for more hardware and protocols, the codebase must expand rapidly to maintain its utility across the industry. The Hadley Center climate model shows a similar trend, but also highlights system rejuvenation. Look at January 2000. New dynamics were introduced, and in January 2008, the ocean replaced. Even in scientific modeling, the files and code count grows as our understanding of the domain or climate physics become more complex. David Parnas coined the term software geriatrics. Software ages for two reasons: failure to update it to meet changing needs, and the fact that changes tend to reduce coherence and increase complexity. The costs are high. Aging software is buggy. Each fix introduces more errors, and performance deteriorates. To fight this, we must design for change and document carefully. So how do we reduce these costs? Let's map solutions to the maintenance types we saw earlier. To reduce corrective costs, we need higher quality code and better testing. To handle user enhancements, we need better requirements analysis and iterative development. For adaptive maintenance, we need platform independence and good architecture. Maintenance is hard for several reasons. First, poor code quality. Opaque, poorly structured, or dead code that does nothing but confuse the reader. Second, lack of domain knowledge. If you don't understand the banking or aviation logic, you can't predict the implications of a change. Third, lack of documentation. Often the code is the only source of truth, and it doesn't tell you why a decision was made. Finally, it lacks glamour. Most engineers want to build new things, not fix old ones. We use three main strategies for rejuvenation. Number 1, reverse engineering. Moving from code back to documentation or higher level design recovery. Number 2, restructuring. This includes refactoring, which is improving code without changing functionality, or revamping, which is changing the UI. And finally, re-engineering. This is the most intensive. It's a round trip where you recover the design, improve it, and then re-implement it with actual changes to the logic. Finally, let's talk about program comprehension. During maintenance, programmers spend about 1.5 times as long studying the code as they do reading documentation. Experts don't read code line by line, they look for knowledge chunks, like design patterns or beacons, which are familiar code fragments. They follow dependency links across the system, whereas novices tend to read sequentially, often missing the bigger picture. Let's start this section with a mental exercise. In reverse engineering, look at this code snippet. We see 3 nested for loops iterating from 0 to n, and a conditional check on 2-dimensional array A. To a computer scientist, this pattern should look familiar. This is a classic implementation of Warshall's algorithm used to find the transitive closure of a directed graph. In terms of domain context, imagine A represents a network of computers. If there is a connection from computer I to J and a connection from J to K, this algorithm discovers that there is a path or a transitive relationship from I to K and updates the matrix accordingly. When you encounter this in legacy code without comments, your task is to recognize the mathematical pattern to recover the high-level intent, reachability analysis. Now let's look at example 2. On the left, we have procedure A. It uses cryptic single-letter variable names like X, Y, and W, and procedures like B and M. It's almost impossible to understand at a glance, but on the right, we see the exact same logic with meaningful identifiers. The domain here is a graphical user interface window management system. The code is handling a focus change event. When the user selects a new window, NW, the system must remove the highlight from the current window's border. Add a highlight to the new window's border. Move the hardware cursor to that window's position and finally resume the process associated with that window. The logic is identical in both snippets, but the version on the right significantly reduces the cognitive load required for a maintainer to understand the system state transitions. Since manual reverse engineering is so difficult, we rely on tools. What can our current technology actually do for us? We can simply use the following: reformatter or document generators, These can take messy code and apply standard indentation or pull out Java doc-style documents to make the source more readable. Code browsing. Tools that allow us to visualize and traverse dependency graphs, essentially clicking through, to see where the function is defined or called. Simple code transformation. This includes refactoring browsers like those built in modern IDEs that can rename variables across a whole project safely, or clone detectors that can find copy-pasted code blocks. This is our first example of a design discovery tool in action, showing a file system view of a project. The context here is OpenMRS, which is a massive open source medical record system used globally. For a developer new to this domain, the tool helps discover the architectural layers. By looking at the folder hierarchy under org.openmrs.api, we can see how the system is organized by functional modules: active list, cohort, encounter, and patient. This directory-based discovery is often the first step in understanding how a complex domain like healthcare is mapped onto a software structure. Next, we see design discovery within a modern IDE, specifically Eclipse. This view focuses on program comprehension at the file level. On the right side of the screen, you see the outline view. Instead of scrolling through thousands of lines of code in concept-service.java, which is another part of the OpenMRS healthcare domain, the tool provides a high-level summary of every method and property in that interface. It shows us at a glance that this service handles things like create concept, save concept, and get concept by unique identifier. By using the outline, a maintainer can follow dependency links without having to read the code sequentially, which, as we noted earlier, is how experts navigate systems. Finally, we have automated design recovery using computer-aided software engineering tools like Argo UML. This tool has reverse engineered a set of Java files to produce a visual class diagram. The diagram provides the context of a simple data structure domain. We can see a main class that likely starts the program, and a relationship between a tree class and a node class. The tool has identified that a tree has a root, which is a node, and each node can have a child, or another node. This visualization allows a programmer to see the static structure of the data, how objects are related in memory, without having to mentally parse the pointer or reference logic in the raw source code.